Hello. So we'll continue with our third lecture of the first week. We have seen some introduction to why we have to look into ordinary differential equations, and then we have seen how some of these things work out in linear systems. So today we will go through proper definition of solution to ODEs. Not the only definition, but something that we can work with. Of course, we have seen this. It's just a recall of how linear systems work, and look at a bunch of examples of nonlinear ODEs and how different they are compared to linear, right? How special compared to linear time invariant ODEs. So before I look at the definition of a solution, we will look at a couple of examples. But let's remind ourselves what we did in linear systems. We have actually shown that we can derive a solution for a given linear time invariant system, whether it has input or output. And we also shown that this particular solution is unique. And therefore, if we wanted to control a particular system, we can do that. Essentially using the closed form expressions that we have, we can easily figure out, well, of course, easier said than done, but at least there is a method, of approach how to achieve a particular behavior of a linear system. Whereas when it comes to nonlinear systems, that's not necessarily the case, and then we will take several examples to understand different kinds of behavior of a nonlinear system. So we'll consider this very simple ODE. This is not quite nonlinear, but given that time derivative of some function x is equal to 1 for all time, then we all know how to integrate this particular equation and claim that x of t is equal to t is indeed a solution. After all, by taking the derivative of x of t is equal to t, will give us x dot of t is equal to 1. Then of course the question becomes basically, is that the only solution, right? We have seen in linear systems by a kind of method of contradiction, we showed that the solution that we derived for linear systems is unique. And then of course the questions like basically how do initial conditions come into picture, right? Do they play any role? Are they continuous with respect to initial conditions? So many questions can come up. And can the solution that we define for an ODE, can it be non-smooth? Can it be discontinuous, and so on and so forth? All these questions come up, and then for this particular example, we'll see what happens. But one of the things that we have to understand is ordinary differential equation. On one side, the left hand side of the equation, you will have a derivative with respect to time. So at least we should be able to define a derivative. So the function that x of t that we call as a solution to the ODE should at least have that derivative with respect to time. Otherwise, it does not even make any sense to call it a solution for a particular ODE. One can actually think of generalizations to that by loosening up our definition derivative itself, but otherwise the standard definition will apply only to the case where we have a certain behavior of this particular function. So we will provide a classical solution, and there are many generalizations of this which we will not worry about too much in this particular course. So what we call a solution to an ODE of the form that x dot equals f of x of t with some initial condition x of 0 is equal to x0, then x of t, the function x of t defined on t greater than or equal to 0, is a solution if this function is piecewise differentiable function that satisfies the ODE to start with, right? And the initial condition itself. Both are equally important and both have to be satisfied. Why should it be differentiable? Well, of course, the fact that it's defined, it's a differential equation, so derivative is a part of the definition, so it has to be differentiable. And then we can survive with this piecewise nature of the differentiable function. In that sense, basically the derivative can cease to exist at a let's say certain number of points. Simple assumption is probably it's not defined in on a finite number of points, at a finite number of points. So what are the various questions that we have to answer? Do all ODEs have a solution? Right? I mean, it's possible that the ODEs do not have any solution. If there is a solution, is it unique? We have seen that in linear systems that the solution that we derived is indeed unique. Of course, what does it mean to all the physics that we are trying to model? What does it mean if the solution doesn't exist, if it is not unique, and so on and so forth? What does it mean to the physics of the problem? And what about if we know how to show, if we know there exists a solution and unique, are there any general conditions that we can derive in terms of the functions of the ODE or the initial condition perhaps that guarantees certain thing about existence and unique? As I was saying, this is one of the definitions. It's the classical, most accepted, and for all practical purposes, this is the only definition that we can worry about in this particular course. But there are more general solutions. Of course, I'm going to come right out and say that some of the solutions may not be necessarily interesting to modeling of physics. They are quite interesting from a mathematics point of view, perhaps not so much in applications. So again, let's remind ourselves things that we have done for linear systems. If we have x dot of t is equal to a times xt, where a is a square matrix, x is some n-dimensional vector function with initial condition given by x sub 0, then we have derived the solution to be equal to this matrix exponential times x0. Of course, this is infinitely differentiable. That means we can differentiate it any number of times. We have shown, through this interesting technique of defining some function, and we showed that by taking the derivative of that function is equal to 0, and then you can go back and look at the video, and we have shown uniqueness, right? And so that differentiability allows you to call this as a valid solution, because that's the requirement we put. It has to be piecewise differentiable. So this is much more than that, and it's also unique. And of course, the solution is linear with respect to the initial condition. That's the nature of linear systems. The solution is also continuous with respect to initial condition. It's linear, so certainly it's continuous with respect to the initial condition. And what else can we say? Some of the behavior that we will look at a later point, if solutions are bounded for a given initial condition around the origin, in a ball around the origin, then no matter what the actual initial condition is going to be outside the ball, it's still going to be bounded. Whereas if the solution is bounded for some point within the ball around the origin, then there are going to be many more solutions that are going to be unbounded. So anyway, over the next several weeks, we will look at behavior of nonlinear systems and how different they are. They're not as straightforward as linear systems. And one of the things that we will eventually learn how to do it is, can specific behavior of nonlinear systems be predicted? And of course, once we know how to predict, can we actually control them? We won't look at so much of how to control. We will look at it a control problem as an inverse problem of this prediction of the behavior. But beyond that, we won't necessarily look at too many techniques that will do control because of the difficulty involved in nonlinear systems in general. So, so next several lectures, we're going to pretty much understand behavior of nonlinear systems, and this lecture will show few examples to start with. So we'll look at this particular scalar ODE. It's a quite artificial. We basically created to show certain behavior. We'll see in a second what that is. So x dot of t is equal to -1 if x is non-negative and 1 if x is negative. So in other words, if you are on the negative side, the derivative is actually going towards positive, and if you are on the positive side, if it's going to go towards negative side, and exactly at 0 also you actually go towards negative. And we'll see something. I'm going to start analyzing this through some simple function. Here I'm going to consider some function of time. Phi of t is equal to square of x of t, where x of t is some solution. We don't know what that solution is. And we conclude that by taking time derivative of this phi of t, and it takes a second, is basically -2 times x dot, but x dot is this -1 or +1, and then you will get essentially d by dt of phi of t is equal to -2 times absolute value of x of t, which is always less than or equal to 0, and of course anywhere other than 0 it is actually strictly negative. And because of that, if we have the initial condition x of 0 is 0, then phi of 0, which is square of x, is also 0. Okay. And because the derivative of a non-negative function is less than or equal to 0, we'll have to conclude that phi of t is equal to 0, and that implies x of t is equal to 0, right? But we do know that x of t cannot be 0 because of the way our derivative is. So in a way, I mean, there are a couple of ways of using the same logic to show that no matter what we try to do, we cannot find a solution that is completely consistent with the differential equation as well as the initial condition, right? Of course, if the question is, do we have solutions for other initial conditions? Perhaps they do, but for this particular initial condition, we don't. And this is, a simple example where we have a case where there is no solution. Of course, does it matter? Does this represent any physics or not is a different question. But for the time being, we do have an example where nonlinear systems for a given initial condition does not have any solution. Okay. So, I say there cannot be any continuously differentiable function because that's a definition of our solution. But we don't have any function anyway. It doesn't matter. So we'll go to a second example, perhaps slightly more interesting one. So this one is even more exotic, but nevertheless is quite interesting, where x dot of t, the derivative of x is actually going to be is equal to 0 if x is rational. It is 1 if x is irrational. So if you look at the real line, basically everywhere the derivative is 0 except where irrational numbers are there. And of course, fundamental questions come, which are more, rational numbers or irrational numbers? That's not the subject of this matter, but the standard assumption or standard, there is a way of understanding the question and then proving eventually that rational numbers are far less than that of irrational numbers. And it's funny thinking basically both irrational numbers and rational numbers are infinite in number. Nevertheless, we still make some way of understanding the size of this in different types of infinities. So we will not get into some of those details, but the question here for us is, can we find x of t such that the time derivative is different for rational and irrational values? And we can find functions that may have this particular behavior almost everywhere, okay, but not exactly everywhere. So we can actually sit down and try and see, no matter what we do, we can never achieve a function that has this nature. X dot is equal to 0 for rational numbers and 1 for irrational numbers. This is one of the examples that we can actually discuss if one were to integrate some functions like that using so-called Riemann integrals, right? So these are very classical examples, and this is we are using it to show that we cannot find solutions the way we defined our solution. Our solution defined here is basically it's a continuously differentiable function. So can we think of one function that actually satisfies almost everywhere? Well, yes. I mean, x of t is equal to 0, for example, whose derivative is 0 everywhere. Unfortunately, that does not satisfy the differential equation, because at every rational number our derivative is 0, whereas our ODE requires that it is equal to 1. So that's why we don't consider that as a solution, and so therefore we conclude that this particular example does not have a solution. So there are many examples where you know, the ODEs can be constructed in such a way that there are no solutions. Now, what is the point of these solutions in this particular regard when it comes to physics problems? The standard assumption that we have is, when we are defining a model, when we are deriving a model for a given physical system, the assumption is that particular model will provide a solution. So therefore, ODEs that do not have any solutions cannot model any physical problem. I mean, if they do something seriously wrong with the physics that we are modeling, right? So, especially when it comes to control problems, and we end up with a case where the control system does not have a well-defined solution, so that means that control will never work in practice. So these are the type of things that we avoid. We don't want cases where ODEs do not have any solutions, either in analysis. It will not represent any given physical system, and certainly not in a feedback control. If we have a closed loop system, if we have a system that has control in it and then it doesn't have any solution, so that means we are in serious trouble. I mean, that kind of control will not work. Okay, so we have seen a couple of examples where we do not have a solution at all. So what about other possibilities? Well, look at this particular again exotic looking differential equation. X dot equals 3 times x raised to 2 by 3. Again, those of you who are quite familiar with the exponentiation and so on, if you think deeply about it, understanding this exponentiation itself is difficult, but we will not get into those details. Let's assume that you understand what they are. But it's such a simple looking ODE. For the initial condition x of 0 is 0, we can clearly see x dot of t is 0 and x power 2 by 3 is also 0. So it satisfies both the ODE and the initial condition, right? I keep saying ODE and initial condition. In reality, ODE means both the derivative equation as well as the initial condition. We'll stop saying that both of them separately. Now, so this is clearly one solution. Alternatively, we can use the standard differential form of differential equations by rearranging dx and dt and so on and so forth, and then by integrating, we will get essentially x of t is equal to t cube as another solution. So you can actually simply check x dot of t is 3t square, and then by substituting t cube into x in the equation, we can see that it satisfies the differential equation, and certainly x of 0 is 0, so it satisfies the ODE completely. So we have in this particular case 2 solutions, right? And both of them happen to be continuously differentiable solutions, so we claim that they are valid solutions. So we have 2 valid solutions, right? So there are many such examples. These are simple enough examples for us to understand it, but beyond that, you can think of ODEs where there are multiple solutions, and sometimes we may not be able to prove that there is a unique solution. The only assumption we can make in that particular case is possibility of multiple solutions. So what's the problem with multiple solutions? We have seen that basically models which have no solution cannot cannot be a model for a physical system. Same thing is probably true for systems with an inherent assumption. The physical system we cannot imagine, at least in the standard framework of things, we assume that they behave in a very well-defined manner, unique manner. So most of the ODEs that have multiple solutions do not become good models for any physical system. So again, same conclusions as before. If we're going to model a physical system, we should not be looking at models that have multiple multiple solutions. And certainly when we put control in the picture, feedback control in the picture, if the overall ODE with the control input, if it ends up being multiple solutions, then again that does not make any sense for the physical world. So these are the things to avoid. So when we actually end up with some ODEs like this, we should stop looking at such models, and the only conclusion is perhaps these are wrong models for the physical problem that we are looking at. So yeah, so there are examples where we can actually construct which have infinite number of solutions. Here we showed 2 solutions, but there are really exotic examples where we can show that there are infinite number of solutions. They are just mathematically quite interesting, but otherwise physically they do not ever make any sense for most models that we describe in the physical world. What about this example where x dot equals x square? Seems benign enough. Here the initial condition happens to be 1 rather than 0 like the previous examples. Again, we will use the standard technique of differential form and then derive the solution, and it gives us x of t is equal to 1 over 1 minus t. And you can check at t equals 0, the initial condition is 1, and then by taking the derivative and substituting in the differential equation there, we can convince ourselves indeed this x of t is equal to reciprocal of 1 minus t is indeed a solution, right? Perhaps we can even show that this is a unique solution. What is the problem with this particular solution? Well, as you can see, x of t is going to be equal to loosely speaking infinity at exactly t equals 1. So that means we have a solution, a valid solution from t is equal to 0 to all the way till 1 without including 1. But exactly at 1 the solution becomes unbounded, and that's a bad thing, right? So what could this mean? Anyway, I mean, a simple remark is basically if you replace your initial condition to some x 0 that is non-zero, then we can generalize this, but then we'll get solution something that looks like this. For all non-zero x 0, we can show that the solution becomes unbounded at some point, right? And what does this mean for physics? Again, most of the problems that we deal in physics do tend to have solutions that start somewhere and then go on and on till infinity, so to speak. So there are 2 conclusions that are possible with examples like this. One, this particular model does not describe in its entirety from 0 to infinite time. So therefore, this, if at all it's valid, then it's going to be valid only till 1 in this particular example, right, or whatever the expression that we have there. So there is certain restriction on this model of its validity, but beyond that it may be unique, it may be continuously differentiable. All those are nice things in terms of validity of a solution and uniqueness, but not in the sense that it is not valid throughout time. And should we consider such ODEs? Well, hopefully not. I mean, one can consider such things, but then this simply means beyond t equals 1, we may have a different model and things like that. Those are the cases where it's quite complex, and then we take some simple models for different times and things like that. But in general, we want solutions where they have solutions from 0 to infinity, right? So anyway, I mean, this example is completing. Basically, if x0 is non-zero, then it becomes unbounded at t equals t0 plus 1 over x0, becomes unbounded, right? So what are the observations from all these examples? LTI models we have seen in the last lecture are quite well behaved, right? Whereas linear time varying models, we have seen them as proxy to nonlinear time invariant models, and therefore even more generalizations like nonlinear time varying models can be quite complex. We have seen that some cases where solutions may not exist, the ODE models do not really represent the physical world in that particular case, such ODE models. Sometimes we may not have unique solutions, and in the last example we have seen that the solutions may not exist for the complete time interval. All such cases we should be avoiding, and then we have to look for systems where all these none of these things are true, or conversely we want ODEs where solutions are they exist to start with, then they're unique and they can be extended till infinity, right? I mean, the ODEs have a solution from 0 to any initial condition and initial time all the way to infinity, right? If that is not the case, then we don't really like to work with such models for actual physical world. So with that, we'll stop this particular lecture, and we will in the next class look at quite a detailed notion of solution to ODEs, and probably look at some conditions that enforce existence of solutions and uniqueness. Okay, thank you.